places over 2 semesters. And because you have a couple Expedition 374 folks here in the room, I basically took all that out of this talk because you may have heard about it already. We haven't done all that much yet. So I'm going to talk about Expedition 342 exclusively here, which I sailed on in 2012. And just to acknowledge some folks right off the bat, obviously the participating scientists, all the technical staff, the crew of the IODP expeditions. I'm going to talk about 342 today. As a U.S. scientist, NSF, obviously, and then all the sponsoring countries of this program. I think there's 15 nations now, something like that, participating in this program. And probably most of you know about IODP, but part of doing this tour, and I'm one of 6 this year, and each year there's these speakers, is to spread the love, so to speak, about IODP. So I have some slides and information about the background of the program, but I'm sure most of this room knows most of that. And then, of course, the students in my group, grad students, undergrad students who have done a lot of the labor and kind of hard work of some of the data I'm going to show today. So I'm a sedimentary geologist by background. So this is how I was trained and used to looking at marine sediments. This is me in Patagonia looking at Cretaceous, deep marine mudstones and sandstones, turbidites and deep marine shales. And so this is how I spent most of my graduate school career investigating deep marine sediments. So coming from this world to then the ship-based world has been really fun and interesting for me. But I just like to show this because this is kind of where I'm coming from. And people that participate in IODP come from all sorts of perspectives. The lab, or even numerical modeling, or other ship-based field work, as well as sort of on-land field work. And so, as you'll see, and as many of you already know, IODP science is really interdisciplinary, which I think is really exciting. I like it. I like it quite a lot. So here's a bit of the outline for this talk. Again, I've been giving this talk at places like 2-year colleges, community colleges, other 4-year colleges. So there's a bit of a primer on ocean circulation and global climate, which at a place like this, many of you could do that much better than me, I'm sure. A little bit about IODP, the latest incarnation of it. It's a 50-year-old program this year, 1968. And then most of the talk about some of the objectives and results in for Expedition 342. And then at the very end, a little bit about how to participate in IODP science. All right, so many of you have probably seen this, and I know physical oceanographers, some of them cringe a bit at the oversimplification of this, right? The global conveyor belt. And but I do think it's a nice visualization for the uninitiated to think about the connection of the global ocean, and at least at a first order, this idea of deep water formation here in the North Atlantic, and this this sinking and southward transport of deep water from the northern part of the North Atlantic, the Nordic seas there, sinking across the Greenland-Scotland ridge here, and then as this pans to the south into the North Atlantic basin. And so the Newfoundland Ridge expedition, one of the objectives was to understand this circulation history in response to some large climate perturbations in the past. So there's Newfoundland, and Newfoundland Ridge sits right here in the path of that arm of what's known as the Deep Western Boundary Current. And as this pans out, this talk I won't be talking about the Antarctic expedition, but so I'll move on here quick. But the other work that I'm involved in with Amelia and Imogen and others is to look at Southern Ocean circulation changes in response to or forcing different climatic events in the Neogene. So as we all know, circulation plays a central role in regulating the planet's climate, supporting marine life, transporting heat, carbon, and oxygen and nutrients through the world's oceans. The formation of deep or bottom waters. So here's a simplified transect from southern high latitudes to the northern high latitudes, sort of in this transect here. These deep or bottom waters form in these high latitudes, the sinking of denser, cooler, sometimes saltier water, and become important components of this overturning circulation system. So I'm a sedimentologist by background and interest and training, and so what I'm interested in is to what extent these bottom currents that impact the seabed can pick up, transport, deposit sediment, and therefore leaving a record of that circulation. Its intensity, its water depth, its sort of temporal history of onset or termination, and so on. And so that's where, as a sedimentologist, I sort of, my role comes into some of this kind of work. I'm not an oceanographer, but is to use the sedimentary record to ask some questions about, make some inferences about deep circulation history over longer timescales. Paleoclimate, paleoceanography in general. I quite like this essay by Rich Pancost a year or so ago. There's obviously a lot of work and discussion about the sort of the tangible values of paleoclimate, paleoceanography, and as sort of targets and modeling and all that important work. But what he's just sort of noting here is also just sort of telling stories from the past, and that's important as well. And so that's a nice, just two-page essay about that other importance that's maybe not as talked about sometimes in our science. Okay, so just to set the stage here, last 100 million years of climate variability, the benthic oxygen isotope curve that many of you see in your sleep probably, that we show in our classes, right? The Ollie Friedrich paper is sort of the most recent that I know of that compiles it going back into the late Cretaceous now. And without getting into the details, this has been used as a proxy for global temperature and ice volume. And so as the curve goes to the left, or higher values in the way it's plotted here, cooler / more ice, and to the right, warmer, less ice. And I'm not going to talk about all of these today, but there's several prominent past events or transitions, phases in this time period that the ocean drilling program is well suited for, that are sort of the focus of a lot of different research. And just to simplify things, red being relatively warm kind of events or episodes, and the blue being sort of cooler ones. And Amelia, see, I took off the other M there for you. Okay, so that's just kind of getting the frame of mind of this longer term as a geologist, paleoceanographer. So what is International Ocean Discovery Program? So again, I know this is review for maybe many of you in this room, but it is 50 years old this year. 1968 was the sort of official kickoff of what was called Deep Sea Drilling Program, DSDP. Initially all US funded, and then not too long after that, other countries, nations became involved, and it's since grown to be even more and more international as the different programs, they've changed names, acronyms slightly, but it has been the same general program continuously for 50 years. And just the basic, why do that, right? It's expensive. It's logistically tough to do this. Why do it? Drilling into the seafloor provides unique and important data and insight that on-land geological studies simply cannot. There just aren't some of these archives. of ocean history available in on land geological archives, or the quality and sort of the nature of those archives. There's different vessels that IUDP uses. The JR, I'd say, is the sort of workhorse. It's kind of like a really reliable Honda Civic that, just like Honda Civics, is getting kind of old, but it's still going. Operated by the US. The Chikyu is newer, operated by Japan. Riser platform, meaning it can drill deeper and into potentially hydrocarbons like an industry drill ship can, whereas the JR cannot. Chikyu hasn't been nearly to as many places as the JR has been over the last couple decades. And then there's other science that neither of these vessels are suited for. So operated by the European consortium, given the name Mission-Specific Platforms, and they'll use whatever we can come up with, sort of jack-up rigs for really shallow water, like the Chicxulub, and other kinds of scenarios where neither of these drill ships are suited. So IUDP and its legacy programs have been all over the oceans. This is probably a little dated data now. 300 total kilometers of core. I don't even know how many millions of individual samples taken since the beginning of the program. You can download this Google Earth KMZ and click on any of these and get a link to the proceedings and to the information. And so one of the messages here is, yeah, it's great to sail and be involved in a new expedition, but the core repositories that house this material is available to anybody to do science. In fact, before I even sailed or applied to sail on an expedition, part of my PhD was using ODP data drilled from the 90s that I sampled some of those cores to do some sedimentological research. So it's just a treasure trove of information for geoscience. This is also outdated now. IUDP likes us to show this kind of thing. A couple of topics in earth science you may have heard about that IUDP has significantly contributed to, I would say. Lots and lots of papers, many of them high impact and important contributions to earth science. The JR, again, is the workhorse of the program. I'm not going to go into a lot of sort of the technology here, the drilling. But although the ship itself goes back to, 1979, I think, something like that, 1980. It's been updated and modernized over the years with dynamic positioning thrusters that talk to GPS to keep it over the site, heave compensator to allow it to drill in up to 12-meter seas. And, it was refit, 10 years ago now, something like that, with more modern labs. And it's constantly being, those are being revisited and sort of updated as time goes on. So just a great vessel for this kind of work. So here's a little video. It's only a minute, and I forgot about it, so I don't know if hooked up to the audio. Can you hear that? Okay, sorry if you didn't hear that. Basically what Shelley, who's a professor at Yale now, this was footage from Expedition 342, is talking about the JR, the Jody's resolution, as a time machine as we drill into the seafloor and get information and samples up on deck. The biostratigraphers, micropaleontologists, can in some cases within minutes or certainly within hours or a day or so tell us where we are in time based on those microfossils, which is pretty amazing. And that obviously can impact the strategy of the expedition as you go. How deep are you going to drill? Get your target in terms of the time period. Do you need to go to an alternate site? And so it's important not just to know as you're going, but it can impact the operations as well. And so just a few pretty pictures for the micropaleo folks of really beautiful forams and radiolarians and coccoliths from Expedition 342. In terms of biostratigraphy, using the life as a recorder of time, the calcareous nanoplankton coccoliths were the most useful. The forams, of course, are the carriers of a lot of the geochemical information that the geochemists have used and are using still to sort of unravel past ocean chemistry and things like that. The other keepers of time, as Shelley called them, would be the paleomagnetists. There's a magnetometer on board, and Earth's magnetic field has known for a long time to have switched polarities from time to time. It's sort of debated about what's really forcing that, but we know that happens. And so you end up with sort of a normal and reversed polarity, and that can be measured, the magnetic properties of the rocks using the magnetometer. And so the PaleoMag or PMag lab group puts together their time sort of scale independent of the biostratigraphy. Then of course they come together and can sort of test and reinforce each other. In some cases the PaleoMag is more valuable if there's not a lot of microfossils. In other cases it's the biostratigraphy that's more valuable, and in some cases, like in this expedition, both worked pretty well and really create a really robust indication of time. And as a field geologist, I was just absolutely thrilled and just tickled by being able to get on my shift and look at a whiteboard and see where we were in time. That, we're in the early Oligocene, or the Eocene-Oligocene transition, late Eocene, and so on. That's happening in near real time. So it's a pretty exciting way to do this kind of science. And I'm not going to go into all the different lab teams on this in this talk, but there's different teams: chemistry, physical properties, fundamental core description, core characterization, and the two I've mentioned that all come together in a very coordinated way. The program and IUDP has really honed this process on board to be as efficient as possible so we can collect as much data, as high quality data as we can. Okay, and I'm happy to talk to anybody after have questions about any of the sort of drilling operations or core lab kind of work. So I do want to spend the rest of the time talking about some of the science that I'm doing as part of this bigger team from Expedition 342. So 342 sailed in summer 2012. It's called Paleogene Newfoundland Sediment Drifts. I'll talk about what a drift is in a second. We started in Bermuda, went to the Newfoundland Ridges drilling area here, and then ended in St. John's, Newfoundland. We recovered over 5 kilometers total of high quality sediment core, spanning the past 100 million years, but really the bulk of it, the majority of it, from the Paleocene, Eocene, and Oligocene, which are the 3 epochs within the Paleogene. But we did get back into the Cretaceous as well. What are the objectives of Expedition 342? A few worth noting here, sort of the primary objectives. looking at the onset and development of Cenozoic glaciation, or at least the impact of that in this area in the North Atlantic. History of North Atlantic deep waters in the Paleogene. Carbon cycle adjustments, the deep North Atlantic during some of these sort of the PETM and the early Eocene hyperthermals, global warming events in those times, and history of land-ocean interaction, oceanic response. And today, and sort of my contribution and role is really focused on this objective here, the history of this deep water formation, bottom current history during this time period. Okay, what is a sediment drift? A lot of geologists haven't heard of a sediment drift. A lot of paleoceanographers are now studying sediment drifts instead of purely pelagic settings, so it's worth talking about what they are. You can go back to at least the 60s, potentially earlier, for some of the first investigations and discussion of deep currents, these called contour currents, so they sort of flow not down the slope but along the slope. These sort of geostrophic currents, this balance of density contrasts with the spinning of the Earth, the Coriolis effect, sets up these large, what are known as boundary currents. And a paper in Science back in the 60s, basically they got a science paper by getting some photographs of the seafloor. Bruce Heesen et al. They wrote this nice paper talking about just fundamental sedimentology. There's a movement of sediment in the deep sea on the continental rise, far from the shelf edge, seeing features, erosional, depositional features, and discussing how that those processes sort of shaped the continental margin. And so these sedimentary systems develop in the deep sea along the bases of continental margins. That's what defines the continental rise in response to these contour parallel currents. And this map here, so here's North America, here we are there. All of these red blobs here would be roughly the major drift, these contourite or sediment drift packages in the North Atlantic. So these are not insignificant sedimentary deposits. These are 1,000 kilometers long, hundreds of kilometers long, maybe a couple kilometers thick of mud, mostly mud piled up. And this is a sort of cartoon drawing from a nice review paper by Robesco et al., just sort of noting continental slope here and down into the continental rise, the abyss, and these large-scale boundary currents impacting the seabed, getting influenced by complex bathymetry, seamounts, or other topographic features. And a lot of this, sort of the physical current behavior of this are certainly not nearly as well known as surface currents for obvious reasons, but there has been some work over the past few decades by physical oceanographers trying to better constrain sort of sediment concentrations and velocities of currents associated with these large contour currents. So we can use these deposits to make inferences about, interpretations about the history of such circulation. So that's sort of the main point of targeting sediment drifts, or at least one of the values of targeting sediment drifts is that because they're a product of that circulation, we can use the character of them to make those interpretations about their history. What do they look like? So here's a seismic reflection profile. These are made from sound waves being sourced, say, from a ship down through the water column. As they hit interfaces of density and other physical properties, they reflect back, and you can produce a record of the seafloor and the subsurface. And so that's what essentially a seismic reflection tool does for us, gives us a image below the seafloor in a cross-section. Just to give you a sense of scale, this is really squished, really vertically exaggerated. This is about a half a kilometer. this vertical bar here, and this would be 10 kilometers. Just so you can see the geometry. In this case, on the Newfoundland, one area of the Newfoundland ridges, here's the volcanic basement, and then all of this between the red and the seafloor, or most of it, would be these drift deposits. This layered material right above the basement would be the initial sort of quiet pelagic sedimentation, and then these fuzzier, sort of more irregular, mounded deposits are these drift deposits. They're made of, depending on where you look, some mixture of terrigenous or land-derived sediment, clay and silt, sometimes sand, and then mixed with pelagic oceanic sediment, calcareous oozes or siliceous oozes. And so they're potentially what you might call a hemipelagic sort of deposit, a mixture of terrigenous mud and silt and oceanic sediment. That's important because obviously the microfossils, which we want for the ocean chemistry and other proxies, are housed in these deposits, but we also have the terrigenous material to link to the physical bottom currents. So how do we see them? Seismic stratigraphy, so acquiring seismic profiles and mapping, which I'll show some results of that. And so the character, at a larger scale, the character of these sedimentary deposits gives us some information about their history. And then core-based work, sedimentology, namely grain size, simply how big the particles are, give us some information about the strength of the currents, especially when those are integrated with other. Just like anything else by itself, there's some questions left by just the grain size record, but when they're integrated with other proxies, it becomes very powerful. Another reason that UDP and other paleoceanographers are targeting contorite drifts, in addition to their circulation record, is that they have higher accumulation rates. They pile up at a faster rate, giving the potential for higher resolution records, right? So if we want to really make some relationships to more recent ocean history, say the Holocene, or especially contemporary change, the resolution of the geologic record becomes important to think about. So drifts can pile up faster, therefore allowing us to get potentially a higher temporal resolution. However, there's a trade-off, right? As the more active those drifts are, maybe the signal you're looking at is more the drift dynamics and less of a regional or ocean basin scale signal. So Newfoundland Ridge drift complex sits here in the path of what's known as the deep western boundary current, or sometimes the western boundary undercurrent, called in some literature, and today is a current that sort of carries North Atlantic deep water from the northern North Atlantic southward. And so from that NASA sort of cartoon, that would be this southward flowing contour current here, known as the deep western boundary current. And so that's why we went to this location, sort of sitting, those drifts piled up in that area for a long period of time, as you'll see. So I'm going to focus on sort of the Eocene and then into the Oligocene. And just to go back to this curve here of sort of global temperature and ice volume, around the sort of early Eocene to middle Eocene, after a period of hyperthermals and relatively warm sort of greenhouse time, there's this long-term cooling, sort of 20 million year long-term cooling, and there's a few excursions here and there, but this long-term cooling, and then there's this step called the Eocene-Oligocene transition right at that boundary there, or the EOT. And so that isotope record suggests an abrupt cooling and rapid growth of continental ice sheets. Amelia and others have studied the Southern Ocean and Antarctica, have done a lot of work looking at sort of the timing of that and testing some of those ideas. And this, is just an artist's sort of rendition of what the late Eocene might have been like. There's debate about sort of the extent and influence of smaller ice caps before the EOT. But there's fairly widespread consensus that after this, the ice cap really grew to closer to what we know of it today. So the EOT is time of accelerated climatic biotic change. Most clearly recognized by this, again, this significant shift, deep sea benthic 4 to 018 and various records from around the world. It's been interpreted to be changes signaling some major global cooling, especially at high latitudes, and rapid growth of ice sheets on Antarctica, and then some debate about the presence or absence of ice in the northern hemisphere is much more tenuous, I would say, than on Antarctica at this time. Some previous studies have, so here's that step. It's going the other way in this plot. The EOT would be there, so 55 to 20 million years. Other studies using water mass tracers like epsilon neodymium suggested that the onset of North Atlantic deep water production coincided with this change. And so that would be this sort of this turnover or this change in directionality here of this proxy. It's been interpreted to be when North Atlantic deep water circulation sort of kicked up or was the onset of that. And so there's lots of literature. I'm not going to go through all of it because I don't have the time. Discussing and interpreting the onset of modern-like Atlantic meridional overturning circulation, or AMOC, at the EOT. Different hypotheses about other processes that are related: enhanced weathering, CO2 drawdown caused by late Eocene strengthening, the Atlantic overturning circulation. And so various papers going back a couple decades or more discussing the relationship of circulation in the North Atlantic Ocean and elsewhere, but I'm focused on the North Atlantic here, in coincident with the EOT, with the Eocene-Oligocene transition and this global cooling. And if you go back to papers from the early 1980s, even into the late 70s, that used seismic reflection data, big regional profiles, mapping reflectors that were interpreted as erosional surfaces. And Greg Mountain and Brian Tucholke wrote this nice paper in 1985 summarizing that work at the time and proposing sort of in the early Oligocene, so this would be the continental shelf going off the shelf into the slope. So this would be very large scale, sort of hundreds of kilometers from shallow water into the deep abyss. And, sorry, let me start here. The late Eocene, sort of a accreting, even prograding continental margin. And then during the Eocene-Oligocene transition, they map what they interpret to be this erosional surface. They named it the AU horizon. It's given other names elsewhere in the North Atlantic. And so they interpreted that this erosional event is the signature of the onset of this vigorous circulation. So this, basically the presence of an erosional unconformity being the evidence for the onset of North Atlantic circulation in the western part of the basin. And therefore, production of, say, North Atlantic deep water at the time. But a major problem with this, testing this, is that most IODP and legacy program sites spanning the EO boundary in the North Atlantic and lots of places worldwide are really condensed, meaning there's not a lot of thickness there of stratigraphy, or a hiatus. There's no stratigraphy. It's missing, right, because it's an unconformity. In which case, the presence of no section there has been used as evidence for the onset of circulation. which is tricky to test, right? So the lack of section has been attributed to the increase in circulation vigor. So this red line would be that time of erosion, right? So you're not accumulating sediment. And so you go from late Eocene into middle or late Oligocene, something like that, across this surface. So one of the major objectives of 342 was to hopefully get a good EOT section. And so I'll show you that today. So I just wanted to just take a step back and just pose a simple question. It doesn't have a simple answer, as you probably already know. Did North Atlantic Ocean circulation intensify at the EOT? So that's the sort of the main question. And so to look at this, me and led by a former student of mine, Pat Boyle, who's now at ConocoPhillips, looked at the seismic stratigraphic data that was acquired to target the site to map the distribution and timing of these drifts. So what you're looking at here, so here's Newfoundland in this inset map, and we're looking at the study area here, the Newfoundland Ridge. It's really the southeast Newfoundland Ridge and this other spur here called the J Anomaly Ridge. And the red and yellow are the 9 sites that 342 drilled. 4 over here on the J Anomaly Ridge, and then another 5 by the seamounts up here on the southeast Newfoundland Ridge. And the black lines are the track line survey of the seismic data that was acquired and then used to target these sites. And so that's needed to target the sites for the science and for safety concerns, but we can also now use those data because we've drilled into them, and we can assign ages to those horizons and map the history of the drifts at this bigger scale. So the next slide, I should say that red line arrows here are roughly the modern sort of water depth extent of the water depth extent of the modern deep western boundary current. The next slide is a profile, this blue line here. So again, 0.5 kilometer there, 10 kilometers across. And so the double kind of blue arrows here are showing the sediment package sitting on top of that volcanic basement. Here's a couple seamounts here. Here's a zoom in. And you can see the drift packages thicken and thin and have interesting morphologies that are, a reflection of their history and sort of the activity of currents. This is a common feature seen around the world in drifts, where next to a seamount you get a sort of local increase in velocity of these currents and creates this sort of moat feature, and then it piles up almost like a levee here as the velocity decreases away from that feature. Just like a stone on the beach, right, where you see little scours sort of form around, but at a much bigger scale here. And so I'm not going to read all this, but what Pat did for his master's was map these profiles around the area, and with the cores that we drilled during the expedition that have really good age control, it's able to assign ages to mappable horizons across the entire area, come up with it's known as a seismic stratigraphic framework. And just a couple examples of some of those profiles of just examples of how that kind of process is done, of mapping these horizons where there's changes in the character of the seismic data, and then tying those to where the cores are and where we have good ages. So we're allowed to, we can get a nice chronostratigraphic framework. And just another example of that between the 2 seamounts here, separated into different seismic stratigraphic units and so on. You can get into the nitty-gritty of that in the paper that Pat led, we published last year. So with that, we can look at the thickness distribution. So now these are maps. The hot colors would be thicker. And so this is a unit that's early middle Eocene through middle Oligocene, 47 to 25. And this is the overlying stratigraphic unit, seismic stratigraphic unit. And so you can see some shifts in where the thickness of where the drifts are thicker and where they're thin. And we can relate that, make interpretations about potentially the shifting of the responsible currents. And so to cut to sort of the summary of that part, if we now look at geologic time here on the y-axis, and these colored lines here would be our mappable seismic horizons that we can map across the entire study area. There's of course more horizons you can map in any one location, but these are the ones that we can map across the entire area. And then those would be the units in between those. And then this is simply a plot. Those isopac maps or thickness maps of a mass accumulation rate of the terrigenous material. And the main point here is that it's low to negligible. And then at 47 MA at this H3 horizon, it's about an order of magnitude increase in terrigenous deposition, land-derived sediment deposition. And so that's interpreted as the onset of drift sedimentation here, and that very nicely, when you look at the cores, you can see this very clearly of going from, beautiful pelagic sort of oozes and chalks to then this sort of gray-green clay-rich deposit of a relatively sharp boundary. So we see the onset of drift sedimentation at 47, about 47 MA. We see a shift in drift sedimentation style from I didn't get into this here, but a more acoustically transparent facies in this unit to this more wavy facies that we interpret as mud waves. These basically large bed forms that form in some drift. And that shift in style, this is all drift here, occurs at this green horizon, about 25. What we don't see is a change in drift sedimentation at EOT. Certainly not consistently that we can map across the area. At any one site, you might be able to see a reflector that could line up with the EOT, but we can't consistently map across the area at that time. And so if we look again at the sort of global temperature, ice volume, proxy curve there, and now all of these little lines here with annotation are different horizons mapped in the North Atlantic to the south of the Newfoundland ridges and to the north. And so our H3 does line up with a few other studies in terms of of a mappable seismic stratigraphic horizon there. Again, we do not map a horizon where others have that are roughly around the timing of the EOT, but I guess I would just caution that some of these, at least a couple of them, aren't really well constrained in terms of their timing. And we just simply don't have enough information about the Miocene. We have hopefully another expedition going back for the Neogene in the future. We don't have enough boreholes in the expanded parts of this unit to really test some of these younger horizons. And then that's our 25 MA horizon, H4. So again, the onset of the drifts correlates with some other prominent horizons in the North Atlantic. Newfoundland ridges lack a mappable horizon coincident with the EOT. And this other 25 MA horizon was not identified in other drift systems. So that's the seismic stratigraphy, but we have cores, right? We have material. So the next approach, and this is from another master's student of mine, Kristen Chilton, who did work with John Yeager during her undergrad. Thanks, John. And Kristen helped me develop some R code to process our data, which I'm still using, so that was a big win. What Kristen looked at was generating a grain size record from this site 1411. And in terms of not having good EOT sections, this is probably, I think, the most expanded marine EOT section in the North Atlantic now. So there's 60 meters of section over 2 million years of time, which for this kind of setting is quite expanded. Site sits within this acoustically transparent drift. We at least don't see seismic stratigraphic evidence for major sort of drifts shifting around and migrating, at least in the seismic data. So we used this site first, targeted this site to look at what's known as sortable silt. I won't go into all the sort of background on that, but basically looking at the terrigenous fraction. So we dissolve away the fossils. I know a lot of you want the fossils. We get rid of them. And what's left is largely, or 98%, the terrigenous material. And then we look at the coarse part of the silt fraction. And so Ian McCabe and others in the 90s sort of developed this proxy called sortable silt, with the idea that this coarse fraction of the silt, the 10 to 63 micron fraction, is that non-cohesive fraction that can be moved and sorted by currents, unlike the sort of sticky clay, which has really complicated sediment transport physics. And so here what we're doing is plotting age from 36 to 26 MA of what's just the mean sortable silt here. EOT here, I should say, is in this sort of light red. And then the abundance, just the mass percentage fraction of 10 to 63 fraction. And again, just for reference, the global compilation of the benthic 4M oxygen isotope, because Steve Bohati hasn't finished the stable isotope stratigraphy. I guess this is being live streamed. He's probably going to see that. That's coming very soon, I've been told. Observations. So I should also say this is just a moving average, this dark black line. You can see the data behind it. I'd love to hear ideas about sort of ways to analyze these kind of data from those of you who are statistically inclined. We see an overall coarsening trend. There's no obvious shift, at least sort of qualitatively, visually, in sortable silt associated with the EOT. Potential shifts, maybe in these younger intervals, 28, 29. And using some of McCabe's really recent work where they measured these currents in the deep sea and then measured grain size, different places, they sort of published this calibration study, current meter calibration study. And although it's difficult to convert something like this to a velocity for lots of reasons, they propose sort of a relative velocity change. If you use that, something like 11 to 14 centimeter per second increase from something to something else, but that would be the change, sort of the delta change in velocity, using that calibration study. And so that record is now sitting there. So Kristen's master's is now all there. In context of the large-scale seismic stratigraphic work, but this grain size data provides this millennial to multimillennial scale picture. However, we're sort of faced with a question, is that could that one site, could that sortable silt record at 1411 be a local signal, right? We can't see it in the seismic data, but if the drifts migrate just through their dynamics, could you see a grain size signal that is not really a regional current signal? So we wanted to look at a complementary record from another site. And so that's 1411 there. And now this is brand new data. Some of it just came out of our lab the other day. So bear with the sort of crudeness of it. But we went to another site, 1406. It's about 250 kilometers away. It's in deeper water by about half a kilometer compared to 1411, in another one of these plastered drifts kind of near the crest of it. It's much more condensed. It's not as expanded as 1411, much more carbonate rich as well. And so different sort of location, different water depth, different facing a different sort of aspect of the potential current. And so we chose this, another EOT section, to sort of get a complementary site. And so, sorry for switching plots on you. We're getting ready for AGU, and there's a lot going on. So now I have time here, 36 to 26. And then terrigenous sortable silt mass abundance. So the percentage of this 10 to 63. The black is the record you just saw, 1411. And the red is this site, this other site, 1406. 1406 is overall more fine-grained. As I mentioned, it's also more carbonate-rich, more condensed. If we look at this sort of preliminary data set, Drew is generating data. This is for my student Drew, PhD student, generating data today, I think. If we look at that in sort of a normalized space where we just scale the min and max values to 0 and 1 respectively, this sort of muted trend here you can't see when we normalize those. At least there's the sort of suggestion of a similar trend with different absolute values, but a similar long-term trend. And there's a lot kind of noise and back and forth in here that sort of the question is there any structure to that? I'm going to leave that aside for today and just talk about this sort of long-term coarsening trend. So at least right now, we're sort of pleased that this other site shows a generally similar long-term coarsening trend to 1411. And then again, just to put it into context with the global benthic 4M delta 018 compilation. So the EO boundary here is this pink line. And this is a compilation of Proxy-derived PCO2, just to sort of have up there for reference as well. So that's brand new stuff. Excited to share it for the first time with you all. I would love to sort of hear your thoughts about that. What Drew is working on, 1411 unfortunately stops there. It's the end of the end of the hole. We had to go to port. We had to leave. It was really sad because we were excited about the best EOT section in the North Atlantic ever, but the expedition was ending, so we had to pull the drill string out and leave. So we couldn't go deeper. 1406 does go deeper and older, and so Drew is looking at samples across this onset, sort of capture that the terrigenous grain size record across that onset of the drifts. So to summarize all this, right, again, onset of drifts at about 47. No significant consistent change in drift architecture or terrigenous grain size at the EOT. There's this change in drift sedimentation style, which I haven't talked too much about, at this 25 MA, and a very interesting extensive drift package in the late Oligocene through Miocene that we're hoping to target in a new expedition. And so that sort of comes to a conclusion. If we're looking at the seismic stratigraphic record coupled with the grain size of a gradual intensification of bottom currents, starting in the middle Eocene. And so, suggesting maybe linked to the onset of that post-early Eocene climatic optimum long-term cooling, right? Going back to, I can just go back a couple, right? From the early Eocene climatic optimum through this sort of long-term cooling here. And so to revisit that question, did North Atlantic circulation intensify at the EOT? At least at Newfoundland Ridge, the records from two different scales and different types of data suggest that deep circulation started earlier than sort of the canonical works from the seismic stratigraphic studies in the 80s, and intensified gradually through the late Eocene and into the Oligocene. And so to sort of finish up, that has implications that we're thinking through, and I'd love to hear those of you with more experience and ideas in some of these hypotheses, like to hear your opinions. But there's been some recent papers, Helen Coxell and others just earlier this year looked at that 1411 site as one of the sites in this paper. And showing nutrient-rich, what they interpret to be northern component water, sort of this North Atlantic deep water, preceded the EOT, came at some point in the late Eocene. And so they, in their discussion, suggest that maybe a probable trigger was tectonic adjustments in the subarctic seas that enabled increased exchange with those northern sourced waters, namely the Greenland-Scotland ridge, sort of the subsidence of that allowing exchange and overflow. In another paper, this is a more modeling approach, which is not expertise, but their conclusions identify the sensitivity to this Greenland-Scotland ridge sill depth as a major factor in the formation of this southward flowing deep water. And so at least recent papers sort of in their discussion talk about, they don't really say gradual, but talk about this pre-EOT changes starting to sort of kick in the Middle Eocene, and because of the sort of slower and not abrupt change is that maybe forced by these sort of subsidence and tectonic adjustments. And so that's something like this, right, where in the Paleocene, 60 MA, and then into the Eocene, that the connection, deep water connection with the Nordic seas up here to the North Atlantic proper. And so there's a lot of debate and discussion about the timing of that, similar to in the Southern Ocean with the gateways, the Drake Passage and the Tasman Gateway, about trying to constrain the timing of the Greenland-Scotland ridge. Here there's a complication that there's also the Iceland hotspot that moves across, and so it may have gone up and down during all of this, further complicating some of that history. And then one final other paper also this year from some workers from Expedition 342, looking at 1404, which is just down the drift from 1406, maybe 20 kilometers or so. That's the orange dots here. So 37 to 31, and they're looking here at sea surface temperature proxies. Amelia can tell you the details about how that's done. That's her expertise. But here they're sort of concluding that, so the green would be in the South Atlantic, southern South Atlantic. So they see this big shift, and whereas in the North Atlantic, this sort of muted or less sort of a cooling, at least in the sea surface temperature, and maybe even a little delayed from the real oxygen isotope shift. And so, they conclude, find no evidence of surface cooling directly coinciding with the EOT. And so another evidence from the expedition, not work that I was involved in, but to sort of try to put together about this story. All right. I've almost run out of time. I think you all know how to participate in IUDP, but if you don't, there's lots of ways. Going on an expedition is awesome and fun, but there's other ways to participate. You could serve on committees. Super fun. There's fellowships for grad students. I've gotten undergrads involved in my lab, getting research experience, working with samples. That's been a really nice thing for students in our department. So there's lots of ways to participate. If your passion is science communication, at least one, if not two, education outreach officers sail on every expedition, which is a really good thing. This is me in the Bremen Core Repository. I mean, the amount of material available to you, to science, to do science is just absolutely astounding. It is now funding, or not funding, but is now the data set for several projects in my group. Cores that were taken in the 80s in DSDP or in the 90s in ODP. I'll send it to you for free. It's amazing. Some demographics. IDP sent me these, which these are just the US participants, I should say, right? It's an international program, but the US gets the most participants because we kick in the most money. So this data doesn't go back very far, but nonetheless, this shows the whole bar is the number of applications. And then the purple part would be the number of invitations to sail. And then by career stage, senior researcher, assistant professor, postdoc, and then grad student. That's really the one I want to point out here. It's the biggest bar, but also getting close to half of the grad students that applied get invited to sail. And so that's also broken down here a little bit differently of sort of career level by senior researcher, grad student, everyone else, about a third each in terms of seagoing participants. And as you might imagine, in 1968, it was a lot of guys, if not all. That's improved over the years. So number of applications, male, female, and then final science party. Again, just the US participants, the other countries sort of have their data. So I just wanted to share some of those as well.
I'd like to say that we reached that while I'm on the staffing subcommittee.
Thank you, Amelia. It's important. There's obviously, that's to keep discussing and keep getting better at as we go, but I think it is worth noting. And sorry to go a little bit over, but with that, I thank you and take any questions.